welcome to this masterclass. It's a pleasure to kind of like, overview the type of research we do here at KAUST, along with colleagues and experts from abroad. So before I plunge into the talk, let me just give a research overview. So basically, my research area is in signal processing techniques, including adaptive, statistical, sparse, and machine learning methods. I work on both theory and applications. And in doing that, I basically use tools from stochastic processes, optimization, linear algebra, and random matrix theory. And the application areas basically focus mostly on wireless communications and localization. But I also work on applications related to smart health and smart homes. So as per the title of my talk, I'll be talking about communication, localization, and sensing. So what I'm going to do, I'm going to divide this into two parts. In the first part, I'm going to give you a glimpse of some of the projects we work on in these three areas. And then after that, I will delve into how this all relates to terahertz. So as you all know, we have an explosion of IoT applications in various areas, smart homes, mobility, smart health, smart agriculture. For example, in smart agriculture, you'd want to figure out the quality of the soil, when it's the right time to plant the seed, when it's the right time to harvest, when certain parts of the crops need to be treated, how humid, like the humidity, the salinity of the soil, etc. So basically, so this is one, for example, application. Your phone itself, contains 20, something like 20 different sensors. A smart car might have something like 70 sensors. In fact, Qualcomm projects that by 2025 we will have around 1,000 sensors per person. Now, these sensors basically need to essentially deal with three issues: sensing, localization, and communication. So what I'm going to do is, as I said, I'm going to tell you some of the works we do in these three areas, and I start with localization. In localization, we work on indoor localization, outdoor localization, and localization in extreme environments. For example, underwater or localization in space. What I'm going to focus on is indoor localization. Now, as you know, we spend most of our time indoors. This kind of got especially so during the COVID, which is hopefully behind us now. The reason now, GPS, which is a wonderful technology outdoors, doesn't work indoors, and there are growing applications that are that require indoor positioning. For example, you need to navigate through a mall. Virtual reality increasingly requires this service. You need to to navigate various drones or autonomous vehicles within warehouses and in smart homes. So it is really required in various applications. So just to kind of for the ones who are not in this area, let me tell you a bit about localization. So in localization, what we do, we're trying to localize a mobile device. We do this by utilizing a few anchors, which kind of measure the range that they have with this mobile device, like in this case D1, D2, D3, and by triangulation, basically they locate the device. Now there are a few issues in doing localization. First, these ranges that are provided by the mobile devices are not accurate; they are noisy. So this can be a source of I apologize again. So these are some of the questions that we need to ask in localization: how to reduce the ranging error, how to mitigate multipath, how to accurately estimate the ranges. Also, you need to track the actual movement, and sometimes you might actually need to deal with to determine the orientation of the actual person. Let me start by telling you how we solve some of these problems. For example, how to deal with removing the ranging errors. We managed to do this by using what's called zero show sequences. These are sequences that are used in synchronizing LTE air interfaces, or also in Wi-Fi synchronization. But it turns out that they're actually very good in doing very high accuracy estimation indoors. In fact, we are able to, with these sequences, we are able to have sub-centimeter accuracy. And actually, we did some measurements that prove this sub-centimeter accuracy. However, when we use these sequences with motion, as you can see here, so what we have here is the red line, which is kind of like you moving over line. We can see that the accuracy drastically reduces, and we have a big error between the actual ground truth and the actual estimated range. However, by using a differential form of these sequences, we actually are able to track the movement very, very, very accurately. And the interesting thing here is that actually these sequences show much higher accuracy as compared to state-of-the-art sequences, and also it allows you to do the ranging indoors with low complexity. Now, another interesting question is actually where you are interested in getting to know the orientation of the device. Let me give you an application where this is needed. Imagine that there is a physician who is trying to do an operation remotely. He is trying to kind of like, operate his or her device on a patient. And so the interest here is not only in the position of the device itself, but actually the orientation of the device. And in that case, the device has to be equipped not with just one receiver, but actually by 3 receivers, because 3 receivers kind of like, define a plane. And by doing that, you are able to figure out the orientation of the device. Now, it turns out that actually the way to solve this problem is using what's called Riemannian optimization. Because here what you have is you're looking for a triangle, in this case an equilateral triangle, and you're searching over what's called the Riemannian manifold of all possible triangles. So if you want, the problem takes the following shape. You have these anchors, our base stations. You have your device, which is basically in this case an equilateral triangle with 3 receivers. And basically the optimization problem that you're trying to solve has this form. You are trying to minimize some objective function subject to the fact that the various vertices of the triangle actually have equal distance to represent an equilateral triangle. So as I said, we use Riemannian optimization to solve this problem. And basically here I am showing the localization accuracy versus SNR. Which is seen here in red line, and basically we are kind of like reach close to a millimeter accuracy in localization. Now, so I have talked to you about some indoor theoretical problems that we have worked on. Let me tell you now about one application where the location and orientation is needed. So this is needed for smart health, and let me show you this video that illustrates the idea.
Tareq, it seems to me that the video is totally unclear. So if you can give the content of this video in verbal way, would be much better for the audience. I'm sorry.
Very good. Excellent. So what we're talking about here is basically the tech neck problem. In the tech neck problem, what we're having here is the fact that basically because of excessive use of mobile devices, laptops, etc., you develop strains in your neck and your shoulders. So and this is a problem that basically office workers suffer from. Now we have around 1.25 billion workers worldwide. In Saudi Arabia, there's 6.5 million of them. Now, and it's basically estimated that around 45% suffer from this tech neck problem. Now, this has been exacerbated because of the shifting to, to remote working. Now, what we're suggesting is basically to attach a device that tracks the movement of your head on various fixtures. For example, your glasses, a hat, or the uqal that's raised traditionally by Saudi men, or by the scarf that's worn by women. That device communicates with an app on your mobile and basically alerts you whenever there is when you have a bad posture. Now this idea basically is part of a startup that has kind of been recognized in various avenues. I have a video. Please let me know, Bassem, if it's clear or not. Okay, this has no sound. It's only the video. Let me know if it is clear or not. If it's not clear, I will. So here's the device on the back of the uqal. It's basically tracking the movement of the person, and is able to tell when there is to alert him when there is actually excessive weight because of incorrect posture. Now, this device also kind of might tell the user to actually go and exercise when he's sitting for a longer period of time. And the device is able also, as you can see here, to kind of track the movement of the head, and is also kind of track when actually the person is moving. And at the end, it kind of provide various statistics, various, for example, exercises to do for the person to deal with this problem. Now, having talked about localization, let me move to wireless communication and sensing. And here we deal with a plethora of problems dealing with space, air, integrated networks. So where we're actually dealing with terrestrial networks, air networks, including UAVs, high platform stations, and also satellites. These basically devices are used in various applications with various mobility abilities and cost distribution, etc. Now, what I want to focus today in the communication and sensing, I want to focus on the interaction between UAVs and IoTs. And I want to focus in particular on how one application that one of our alumni, Dr. Osama Bushnaq, has worked on, is basically how UAVs and with the help of UAVs can help us detect fires. So we throw these IoT devices in low-cost IoT devices in the forest, and basically they can be turned on or alerted whenever a fire is detected. However, because they have to be low cost, low battery, and they are in the middle of nowhere, they have no way of communicating this information into an actual into a central, into the authorities. So what the UAVs do is they actually roam around the area, collect information, and kind of alert the firefighters early enough so that the fire can be contained. Now, the big issue here is not the data collection, but actually the big issue is optimizing the number of IoTs, the number of UAVs, and the UAV path. At the end of the day, you want, with a limited budget, be able to alert the authorities quickly enough, while minimizing the amount of loss. So here we are able to kind of characterize the number of IoTs needed, the number of UAVs needed, and actually the actual path that needs to be taken. Now, there are two issues with using UAVs and IoTs. Both are power limited. So how do we deal with this? Well, this is something that also Dr. Osama Bushnaq worked on in his thesis. And basically, how can we deal with UAVs that are power limited, but not only power limited, but actually backhaul limited? How can we allow them to kind of like, because otherwise what needs to happen is that, for example, these UAVs, they need to go back, get charged, or they need to also their backhauling capability is quite limited. Not only do we need them, for example, for the fire detection example, but also to cover events, major events, like, for example, a major a football match or a concert, which happen every now and then, and there is no need for fixed architecture or fixed base stations to actually cover these events. So the solution that we talk about is basically using tethered drones. The tethered drones is basically like treats the UAV like a balloon that gives it infinite power supply, so it doesn't need to be charged, and infinite backhaul capability. So in a way, this kind of solves the power limited issue of the UAV as it's, for example, dealing with IoT sensors. Now, as I told you also, the IoTs themselves can be power limited, and this is another example of how we dealt with through the interaction of UAVs with IoTs. So in this example, which is basically done by Omar Khalifa, who was an intern in my group last summer, and mentored by Dr. Noor Quzaiha. In this case, what we did is the following. The UAVs are not going to only collect data, but actually they're going to prolong the life of the IoT devices. They do so by actually waking up the devices whenever they are needed. So if you can see in this pictorial here, we have the IoT device. It has a wake-up circuitry. So the IoT device, in most cases, is in dormant or sleeping. Whenever the UAV hovers over the IoT device, it wakes it up, and so the IoT goes and produces the data transmit the data to the UAV and goes back to sleep. And in this way, not only do we collect data, but we actually save the battery of the IoT device. I have a video here, but I'm afraid of the quality of the video, so I'm gonna skip it. But I want to mention here that, for example, this kind of results in power saving. So, for example, the IoT device, when it is in full operation mode, it consumes 20 milliamp, while it is in the sleep mode, it will consume only 3 milliamps. So let me end with one last smart sensing application. So this case is related to use of to the conservation of water. In our part of the world and the Muslim world, we basically like do what's called ablution or wudu before prayer, and we do it 5 times, where we wash various limbs of the body. Now, it turns out that when we do this, 60% of the water actually does not get used. It goes all the way from the tap to the drain. And if you make the math, you know that you will find out that actually 8.4 billion liters of water is actually wasted in Saudi Arabia alone. Now, this is a significant issue because in Saudi Arabia, most of the water is produced by energy-hungry desalination. Now, you can say, okay, you know, there are the IR taps, but actually the IR taps have their problems. They need to, and you must have faced it. You might need to learn the response pattern of the tap, actually, because it might turn on or off at inconvenient times. When you want it to turn on, it doesn't, and when you want to turn off, it does not. In several cases, it's also sensitive to light reflections. So our solution, which is basically kind of like, you know, led by Abdullah Filimban, is what's called the smart tap. The smart tap is based on a camera or a depth camera that basically tracks the movement of the person and the joints of the person, uses AI to actually sense when this person is actually using the tap, so as to turn on or off the tap. It might even also modulate the amount of water that's being used to make sure that actually so that depending on the quantity you need. So, for example, washing hands might require less water than washing the face or washing the limbs. So this one is done through artificial intelligence that's kind of communicated through the cloud so some of the calculations might be done over the cloud itself. I have some a demo here that demonstrates the difference between the IR tab and as you can see, the IR tab is not always responsive. Not responsive here, for example. You have to kind of like trigger it to respond. And this is basically the smart tab. So as I said, it kind of tracks the joint of the person. And it's able to stop exactly when stop and start when it's needed in a seamless way. Okay, so to summarize the first part of the talk, I have talked about various applications in localization, communication, and sensing. Now, as the title of the talk suggests, we're talking about the convergence of these services in terahertz systems. This work is basically ably and mainly done, led by Dr. Hadi Sarieddin, and it's a joint work with Professor Salim Alwini. So the big question is, why do we need convergence? Why these services that I just talked about have to converge in terahertz systems? Well, first of all, let's establish some facts. First of all, as we all know, the number of subscribers is increasing by the year. The internet traffic itself is, as you can see in this figure, is exponentially increasing. So we are reaching the capacity of limits of wireless networks. In fact, that's the reason why we go from one generation into another, starting from 1G all the way to 5G. And if you can see, basically, we have every 10 years, we have a new wireless standard ending with 5G, which started to roll out in 2020. However, we expect more applications that are data hungry and that are latency sensitive. For example, e-health, extended reality, AI, industrial IoT, autonomous driving, etc., etc. All of these are even more data hungry, and so we need to actually ways of increasing the data rate and reducing the latency. And so this is where terahertz comes into the picture, because actually in all of the 5 generations that I alluded to 2 slides ago, basically only uses less than 1 gigahertz of the available spectrum, while lots of the around we have spectrum all the way to 10 terahertz. Now, physically speaking, we cannot use all of the spectrum, but a substantial part of that spectrum is still possible to use. And so a plethora of applications, from satellite communications to interchip communication to body-centric network communication, can utilize this spectrum. So many more applications at much higher data rates are possible. Not only that, but actually localization, which I talked about, also benefits from that. So if you rely on terahertz communication, you have much higher frequencies, so you have tinier wavelengths, narrower beam widths, and so this allows you much higher angular resolution or localization accuracy. You have also higher bandwidth, so which allows you to have much more delay resolution, and so your ranging accuracy that's needed in localization is much higher. In fact, you can even go into environmental maps. So not only do you localize people, you are able to map the whole environment, just as done in for example, in LiDAR. And what's more is because the wavelength is so small, and the footprint of the terahertz devices are going to be very small. Localization becomes a prerequisite for communication. So if I want to communicate, for the transmitter needs to communicate with the receiver, it needs to know the location of that receiver. So localization doesn't become just a service, it becomes intertwined with communication. And that's what we call about convergence. So what happens is basically the merging of all of these services, communication, sensing, and localization. Now, for terahertz, which is expected maybe 10 years from now to kind of be rolled commercially, perhaps to happen, there are several challenges that need to be dealt with. First, we need devices. We need transmitter and receivers that operate in the terahertz range. Now, this is not the type of work that I do, but this is the type. These are what other labs are working on. There are several contenders, for example, electronic, photonic, plasmonic solutions. But we're hoping as systems engineers that by the time these devices are needed, they will be available, just like as happened in millimeter wave of the 5th generation. So this is the first thing. Devices is the first challenge. The second channel is channel modeling. We need that as systems engineers. We need it for standards. We need it for signal processing. We need it for even the MAC layer protocols. So we need to, for example, characterize key parameters like the path loss, the fading, the blockage effect, which is quite pronounced at these high frequencies. I want to in particular focus on path loss, which is basically highly pronounced in this case. So if you can see here, I'm plotting the path loss versus frequency, and what you can see is that with increasing distance, we can actually having increasing much higher path losses, and the same goes also with higher frequency ranges. So how do we deal with that if you're going to do like proper communication? Well, it turns out that we have to rely on massive MIMO. So a single antenna will not allow us to actually communicate with the enough power that's needed. Or the antennas that what we need would be quite bulky, that will be not useful for our handheld or mobile devices. And they might not be even okay to use for safety guidelines. They could be used in backhauls, okay, for the backhauling, but for mobile equipment, we need massive number of antennas, which allows us through beamforming gain to actually reach the required gain to combat the path loss that I talked about in the previous slide. So as I said, the second challenge is understanding the channel. And this is actually what we have done in our TeraMIMO simulator. It's a simulator that allows you to simulate the terahertz channel from end to end in a 3D end-to-end modeling, including issues like the line of sight, non-line of sight, utilizing the antenna architecture, taking into account things like molecular absorption, misalignment, planar and spherical wave propagation, time variation of the channel, etc., etc. So this is as I said, a simulator that's available on GitHub. It has a very friendly GUI that you can use to play with, and it's able to actually generate various results that are very important for us systems engineers to be able to do the various designs that are needed. So for example, using the TeraMIMO simulator that I told you about, we can simulate the path loss versus frequency for different distances. Okay, so in the remaining part of the talk, I'm going to talk about 3 issues that are faced in terahertz communication. The first thing is molecular absorption. So what happens, I showed you this figure before, and I alluded to the fact that path loss increases with frequency and distance. And what's more is that actually you start noticing that very high resonant frequencies, like where the path loss becomes almost infinite. This is because of molecular absorption. So basically, certain gases in the atmosphere result in interact with the terahertz waves and basically reduce their effectiveness drastically. Now, this is problematic for communication because you have to fragment the bandwidth that you have. You have fragmentation. This is also problematic for localization because you need to basically kind of like, have certain bandwidth power allocation for different dense distances in that you're trying to localize. However, it is perfect, something perfect for sensing. Why is that? Because different materials and different gases actually have different spectral fingerprints. So here, what I'm showing you, I show you the spectral fingerprints of various materials like chalk, like aspirin, like, for example, baking soda. And as you can see, they have different fingerprints. And so this allows us to sense them. If you use massive MIMO as, in addition, a massive number of antennas, you can actually sense them at a distance. And the same thing can be said about gases. So here we have various fingerprints for various gases. So here's an example. Now, in addition, what you can do, you can actually piggyback the sensing over communication. So the same signal that you are using to communicate data is actually used for sensing. And this is another example of the convergence of these two services. Another issue, a second issue that is faced in signals that deal with high frequencies is blockage. So while this is something that we don't experience, say, in our cell phones or like Wi-Fi, it turns out that as the frequency increases, blockage becomes an issue. Blockage, be it walls, be it humans, and so this needs to be dealt with. For example, one way of dealing with it is, for example, if you have the access points on the ceilings, so that there is minimal number of blockages. Another way of now turns out blockage is not only this also affects coverage, because if you have blockage, then the coverage will be affected. In fact, blockage even happens in outdoors. So the coverage probability will vary with the height of your devices in the atmosphere, how high they are in the atmosphere, and they will also be affected by the season. So say a more humid summer season will be counterproductive to terahertz as opposed to, for example, a winter season. Now, another way of dealing with blockages is basically like, where you actually use a hybrid of RF and terahertz devices. And this is a work that's led by Dr. Noor Quzaiha in our group. So what you do here is basically the following. You have a number of access points. Some of them are RF, so they operate at lower frequencies, and so they have a higher range. And some, and the other fraction are operating at the terahertz. So they have a lower range, but because of the high bandwidth, they have a much higher rate. And so what you need to do, you need to strike the right balance between the number of RF transmitters, which have a higher coverage, and the number of terahertz transmitters, which have a higher rate, so that you can get the best of both worlds. Let me show you some simulations here. This shows you the coverage probability versus the fraction of terahertz access points we use. So we can use between 0 and 1. As you can see, as we use more and more terahertz access points, the coverage probability actually reduces because of the path loss and because of the blockage issue. However, when you look at the actual rate, what you notice is that the more a terahertz transceiver you use, the higher the rate. So there should be a balance between how many RF and terahertz receiver you use. Now, another issue that affects drastically terahertz is the non-low enough side channels. So the terahertz channels are they're almost like light in nature. So they have very few multipaths or non-line of sight paths. Now, non-line of sight only channels are not good because they are so weak because of the path loss. So, but when we have a line of sight channel which is assisted by non-line of sight channels, then this is kind of like a good thing, because this creates a richer MIMO channel. So non-line of sight channels or non-line of sight assisted channels is good for communication. They are also good for localization, because this allows you actually to have more kind of like, feel of what the environment, and actually you can see what's called around the corner. You can see around the corner. So non-line of sight is an issue in terahertz and needs to deal with. Of course, having more non-line of sight or being able to resolve more of sight doesn't come for free. It has to be, we have to actually have increased complexity, computational complexity to be able to deal with it. Now, one way of artificially increasing the non-line of sight is by using what's called reflective intelligent surfaces. So if you can see here, I have a transmitter and a receiver. There is a line of sight between the transmitter and receiver. There are non-line of sights here that you can see, the two here, but for some reflectors. And we artificially introduce some non-line of sights through the reflective intelligent surfaces. So these are basically alternative infrastructure enablers to MIMO, and they allow us to extend the communication range of our terahertz systems, and also they allow us to enhance the localization capability. I will end with one last problem or challenge with terahertz, which is basically the narrow beam. So as I said, because of the use of the massive MIMO and the large array gain, you actually have very narrow beamwidths. Now, this has some advantages. First, it reduces interference between users. It results in higher security, and also it's very good for localization. It gives you a higher angular resolution. However, it has its own problems. First of all, misalignment between the transmitter and the receiver. So as you can see here, the transmitter and the receiver are somehow misaligned. So this results in link delays the link establishment and causes deafness. So meaning, like, the receiver cannot hear the transmitter, and it gets exasperated with movement. And this basically tells you why localization is important for communication, because unless this alignment is established, you cannot actually go ahead with your communication. So as I mentioned, misalignment gets affected by movement. So here, the localization accuracy itself gets affected. So here we can see the expected antenna gain versus the antenna motion. And as you can see, the higher the movement, the less the gain. Also, like, the alignment gets affected by distance. So misalignment in 20 meters is misalignment in 100 meters is worse than misalignment in 20 meters. So this brings me to my final slide. I have talked about the IoT Internet of Things, and how they kind of are dependent on sensing, localization, and communication. I have mentioned to you some of the works that we have done in sensing, localization, and communication. And basically, I have tried to convey the message that as we go to the future, as we work on 6G, we need to go to the terahertz band, which have its own advantages and challenges, and also like potentials. But in this band, one thing is certain: you expect these services, these localization, imaging, and sensing, which were only services on top of communication, you expect them to converge in the terahertz systems. Thank you very much.
Thank you very much, Tareq, for this interesting and comprehensive talk. And the audience have raised basically quite few number of questions, but I could categorize them into 3 different parts relevant to your talk. So they are in localization part, and sensing part, and the terahertz part. So the first question that was raised that is relevant to the localization part, an audience asked a question: does altitude or the G values considered in localization? So he basically means, is it possible to get the altitude values for the device?
Yeah, I mean, yes, this is exactly what I was talking about. So latitude means, I assume that he or she means orientation. So that's what we're trying to do by actually having more than one device on the same by having more than one receiver that kind of constitute a plane, we are able to kind of like, figure out the orientation of the receiver. This is definitely needed in, for example, say in UAVs, in aviation. But I gave an example of remote surgery where this is also needed.
Okay. So a second question that is relevant to the sensing part, an audience asked a question that is morely relevant to the deployment part. For example, he asked that if I have a very vast area, like he's talking about 80 acres with different type of people, lives like campus, residential, farming, and all that stuff, how he can possibly sense the total activities in such an area with such a diversity?
That's a very interesting question. I mean, it depends on what the purpose is, but maybe this kind of like, allows me to talk about another, one way of doing it is actually through remote sensing or through cameras, etc. But actually, this is kind of another work that we're doing in our lab, is basically trying through RF signals that are emitted by your phone to actually try to characterize the behavior of people. So, so you could do it through, say, remote sensing, through, for example, you could do it through cameras, which are expensive, but you could also, like, do it through, say, like, the RF signature of your mobile device that's sensed at the base station. And this is kind of like a low-cost way of doing it. Now, at the end of the day, it depends on the application. So unless I have more specific, details, I cannot really answer.